Okay, this slide is important. This one, this slide. This table is summarized almost half of the chapter 9. Right. So before your assessment or before your final exam or even test 2, you need to understand or you try to memorize the term here and the reaction here. Right. On the left hand side here, just a graphical diagram. Right. Okay, so this table is important. Then previously, last week we stopped at example. We stopped at example 7, right? So example 7, right? So by now you should able to identify pro something, like for example on the slide here, pro-eutectoid, pro-eutectic, and so on. So that's why before we start, I show you the table. The table is very important. Okay, today we go into slow cooling of plain carbon steel. Steel phase diagram. On the left, temperature. On the x-axis is percentage of carbon. And for ion carbon system, the maximum we go is 6.67% of carbon. And recall why 6.67%? Because we're dealing with alpha, gamma, and Fe3C element. We have BCC structure, FCC structure. Okay, so it's because of the crystal structure and the temperature changed the crystal structure. Right. Here, before we go into the diagram, you look at the diagram and identify what are the phases or what are the elements that you have. So you drop from the top, you come in from the 1000 degree, then you slowly cool down. So you have a gamma, then you drop, you will meet alpha plus gamma. Then on the other side, you have gamma plus carbon. Right? Then here have a very, very small portion. You can get 100% alpha, very, very small. Right? And then as you drop your temperature further, you get alpha plus carbon, Fe3C. Now we learn eutectoid. Eutectoid. So if a sample of 0.77% eutectoid plain steel carbon is heated 750 degree and then maintain the temperature, the structure will become homogeneous austenite. The process is called austenitizing. Okay. So what is this statement important? This one, normally in the assessment, it will come in the section A. It will ask you about definition, or how you achieve a certain process, right? So this one, if the question asks you define or explain this process, so a few keyword here, temperature, and then what happened to the structure. Okay. If the process is cooled down very slowly, just above the eutectoid temperature, the structure will remain authentic point here, right? At this point. So it will come in from 1000 degrees C, slowly down, and then you maintain at 750 degrees C, about here. Then you cool very, very slow about this area, then you will reach point A. You further drop the temperature to the eutectoid temperature or just below it, will cause the structure transform from austenite to laminar structure. Right? From A, it will drop past this point. Right? So point B, you will have a structure called pearlite. Right? Pearlite is a eutectoid structure. So the name pearl is because you will see the same characteristics as you can see in the nature pearl. Huh? You see something like that. Then next one, you look at the diagram. We look at alpha, and Fe3C change very little from 727 degrees C to room temperature. So it changed very, very small from here, from this point, 727 degrees C, and then until here. Here, if you zoom in, it still go in a little bit. So the small region here is tell you how you get the alpha. Correct. Huh? Okay. Then we show you another diagram. If you compare side by side, this one is iron carbon of eutectoid for 76% carbon. Huh? Okay. So this is like the same, actually the same. Just show you. Then hypo eutectoid. Hypo is somewhere on the left. Hyper is somewhere to the right. Right. So you see the word hypo is somewhere to the left. So if the sample less than or 0.4%, so if you look at the diagram here, let's say we pick this point here. So 0.4% still, hypo-eutectoid still. Why hypo? Because we choose the left-hand side of the graph. It's heated 900 degrees C. We pick one point here, 0.4%, and then we start from 900 degrees C. The structure become homogeneous again. So you see the word homogeneous, and then you link to the temperature. As long as in the steel, you heat at a certain temperature, then you maintain it, you get a homogeneous structure. Okay. Then if you cool down from 900 degrees C, you cool down to a temperature just above the 727 degree. So here we pick 1.700 something that it passed from gamma into alpha plus gamma region. Right. So here you would get a pro-eutectoid ferrite for nucleus and grow most at this one. So pro-eutectoid means the first grain of eutectoid happen. So here you get gamma, and then it slowly reach this point. So after this point, the first alpha will grow from after it passed this blue line. Okay. So again, if it land on this blue line, it can be either alpha or gamma. But this line, again, is very, very thin line. So the question will sometimes will ask you what happened before and after. It will give you plus T and negative T. Plus T means above the line, negative T means below the line, because it's cool down, right? So here you see the word pro-eutectoid start to grow. Then from B to C, the carbon content of the remaining alpha will increase from 0.4 to 0.77%. Okay, B to C, your alpha will become more and more alpha here, right, as you drop. So here you drop this line, gamma, then pass this line, more and more alpha will grow here. Okay. So B to C, how we know this statement is correct? Why your alpha grow from remain, right? It will increase. So you drop this line. If you C point, you drop further a little bit, or you just draw a straight line, a vertical straight line. C you drop down, you get 0.4. You draw a horizontal line, you drop down, you will get roughly 0.7. Then you drop further, you get 0.77 if you meet this point. Okay. Then at that point, at this straight line here, this straight line in the carbon system or iron carbon system, this line, you get perlite. Okay, you get perlite. So there's an equation at this straight line here, 727 degrees C. You will convert alpha austenite. Sorry, you convert austenite to ferrite plus cementite. Yeah. Okay, this one is alpha. So after you pass this line, after you pass this 727 line, you will get eutectoid. It's a bit different from the previous one. Pro-eutectoid. Pro-eutectoid is here. The first grain that grow alpha. After you drop temperature from gamma, pass through this blue line, very near to B, just past this blue line, you get the first grain. First grain is called pro something. Okay. So again, don't don't go and mention pro something at the very end of the line. You won't get pro something here. You'll get pro something near just below the line here, something near below here, something near below here. Okay, you get pro. So this is another diagram that's similar. You just squeeze the format of the graph, right? So you can see the schematic diagram. If you drop from a certain weight percentage of carbon, so this line, so you know that this on the top is gamma, then drop to here is alpha gamma, and here is alpha plus Fe3C. So the first one you get all 100% gamma. Then you pass through the red line here. Point D here is alpha. Alpha will start to grow in the grain between gamma. Okay, it will start to grow. So this is this here start to grow here. So when you get the first drop of alpha, that called pro-eutectoid something. Huh? And as it drop further, this grain, red color grain, will grow along the grain boundary here. So you see there's a red color growing. Okay. Then when you pass this 700 something, there's a eutectoid temperature. You pass this one, you'll get like a zebra crossing, or call it perlite characteristics. So you draw the pearlite characteristics, the zebra things, then yeah, then you put in the alpha, put in the Fe3C and so on. Okay. So when you draw a diagram, look carefully on the phase diagram, which region you have. So for example, point F don't include the gamma here. Don't include gamma inside this diagram. Because this region, after this temperature, you won't see any gamma anymore. This region, you will only have alpha and ferrum 3 carbon. Okay, so be careful on your diagram. So then the next one, I think this one is the same, right? The same, only try to observe what happened to the element. So let's say you're given one number of the weight percentage of a carbon, then you explain what happened. So that is usually the assessment will ask you to explain. Give you one straight line and then label A, B, C, D, explain the process from A to B, A to certain point. So if you're given 4 points, so you will get like 8 marks. So each point you explain what. Then you draw this diagram, then you just give it what element is it, right? So here A, this region you see gamma, so you just draw and then draw gamma, gamma, gamma. Then when it pass this point, then something start to grow already, right? Something start to grow between the boundaries here. So here it passed through, and then you look at the phase diagram. Here you have a Fe3C. So you go to the boundaries between the gamma, you fit in the Fe3C. Then you drop down, then you pass through the pearlite eutectoid things, then pearlite start to happen, right? Pearlite start to happen. Okay. Okay, what I need to highlight is that for carbon steel, means carbon plus ferrum system, pearlite is very important on this word. And then you should understand at what temperature or after you pass through what temperature, you get pearlite. So normally it pass through the eutectoid temperature. In this case, it's 727. For carbon steel, 727, this temperature is important. Okay. The rest you read is still the same like the previous few slides. Okay. Yeah, it's still same. Okay. Okay. The rest you read. Same graph, you just change the colors and the scale only, right? Again, what I need to highlight here is, do you know how to draw the figures in the circle here? If you're given a one concentration, a certain temperature, slowly, are you able to draw this diagram? So you look at the phase diagram. From first point, what you have, you draw the component. Along the boundaries. This boundary you have gamma plus alpha beta 3 carbon. 3 carbon at the boundary. Here to here is a bit different from the top and the bottom. So top one you can use very small dot, but when you reach to the eutectoid temperature here, this one will become something like pearlite, but very, very thin purple color along the boundaries. Then pass through the eutectoid, you get a pearlite structure. Okay. Okay. So this is a complete graph for iron carbon steel. We call it iron carbon steel equilibrium diagram. So you explain the whole carbon steel diagram. So this is a very important graph for you to observe. All right. Lots of information here. So when you do revision, you try to observe what are the region you have, and then the name of the chemical. For example, the symbol gamma, what is that? Gamma is austenite, alpha, ferrite, delta is what? CM is cementite, and so on. And then where is the hypo? Where is the hyper? Right, hyper. Then after 2%, it becomes cast iron already. You add more than 2% carbon, you get cast iron. Okay, I think the rest is quite direct. Only add in the name for you, right? Yeah. Okay. Then I need to highlight the crystal structure that you have, right? So in your gamma steel, you have what crystal structure it is? FCC, yeah. Then when you drop, you get alpha. So you get rich gamma is here. Gamma, this is FCC. And then alpha on this graph is somewhere here. We start to change from gamma to alpha. Over here, you start to see BCC crystal structure. Then cementite is a bit complex here. This is another one you also can download from the tutorial question, right, or from my slides. A lot of information is there, but basically we already summarized in the previous few slides. This is it's like encyclopedia. What are the crystal structure you have in there? If you work in the metal steel fabrication factory, then this will be your encyclopedia lah. Will be your Bible lah for your job lah. Okay, so let's look at how we apply all the information. So you're given a chart, and this chart you see ferrum and carbon, and the carbon is until 6.67. Okay, then the temperature you're given, your temperature here, what you see here is 900 something, 727. And then you know that after 727, you get polite. Then here is alpha. Even though the question don't give you, you know that here is alpha. Okay, what else? Okay, how do you guess alpha? Gamma drop, you get alpha plus gamma, you start to see alpha already. And then you drop further, this region, you get alpha, ferrum, carbon. So they must be changed to something that exists between these two, right? So it won't have a gamma here because already changed from FCC to BCC already. So here you only have alpha. Okay. Okay. So you read the statement. So you have a eutectoid plain carbon steel was slow cool down to the gamma region. To room temperature contain 9.1% eutectoid ferrite. Assume no change in the structure on cooling from just below the eutectoid temperature to room temperature. What is the carbon content of the steel? Okay, so how do we start? So we don't know how many percent of carbon. From the question, we don't know where is our X percentage. We don't know, right? But we know that we are at a hypo-eutectoid steel. Right, so this highlight 727 is your eutectoid temperature. Right? So we'll use the equation that relates eutectoid and pro-eutectoid equation. So the total ferrite alpha that you get is pro-eutectoid ferrite, means the first grain that grow on the phase diagram, pro-eutectoid ferrite plus eutectoid ferrite. So you want to get where is your alpha, right? What is the total alpha you have? Okay, then here we rewrite the equation. We take our eutectoid, we remain our eutectoid, we pull pro-eutectoid component to the left, we get minus. Then we use level rules. Here, 0. So here, 9.1 weight percentage. If you get the ratio, right, you get 0.91. Right, if you want to get level rules, so you get 6 point something. So this is a eutectoid point. Then you want to get your alpha, right? You want to get your alpha. Alpha is here. So you know level rules. Level rules, you have 3 points. 1, 2, 3. You want to get here, divided by this one, you get another side. You get here to here, divide by total length, you get another side. Make sense or not? You get this one, divided by total length, because this one is opposite of this point. So this one is referring to alpha here. Make sense or not? Okay. So that's why we use the last point minus the x. We don't know where is our x, but we know that we want to calculate the ferrite component. So this must be somewhere between here. So we get this one minus the point of interest divided by the total length. Okay, this is the total ferrite. Then this pro-eutectoid is 0.77% minus x divided by 0.07 minus 0.02%. Okay, so this is to find the weight percentage. Okay, so you're playing with the three point that you already expert for level rules. So you just want to guess where is the weight percentage. So here you only have one unknown. You do the arrangement of equation. You solve for x, right? Right. So you get the x is 0.97% carbon. Right. So here on the slide, I just highlight in the exam, show the working. So the working on how you get your answer. Okay. Means if you need to, if you have a quadratic equation, then you show how you find the root. Okay. Any question on example 8? This is a reverse engineering, reverse the information. Okay. The previous example, what you see, we feed you information before the process, but example is the one that we work backwards. Okay, now we start to go into what happens if you have heat treatment. Just now we see that if you drop temperature and then you hold, you get homogeneous. Now how we make use of the temperature? So we start to use heat treatment. Okay, the first type of carbon steel we will get martensite. So how we get martensite? So here on the phase diagram here, we have a ferrum carbon. We will use rapid squinching. Squench or squeeze means you drop into the water or you cool down. There's a liquid for you to drop and then you take the metals out. So here you have gamma. You have gamma plus carbon. You have a alpha carbon, and you have a few region here, and then your carbon percentage up to 0.6. Okay, then you have a martensite here. You have a few type of martensite. You have a lard martensite, you have plate martensite. So if your gamma rapidly cool to room temperature by squinching in water, the structure will change from alpha to martensite. So you should have a gamma first, then you drop from any place here, you'll still get, at the end, you'll still get martensite. Okay. So it looks like this one on the under microscope. Huh? So this is more on the crystal structure. I won't test you on this. I won't ask you on this. So it just tell you that what happened or how martensite form. Huh? Okay. So it means within this is for martensite crystal structure. So here you have a loss of carbon will grow inside the thing. This structure is called BCT, body-centered tetragonal. I want to ask you how to draw this one, unless you do material science. Your major is material science. Okay. Okay. Important is that you know how you get martensite. You rapidly cool from gamma, then you drop down to room temperature. Okay, then on the graph here, you have a MS, means you start to get martensite. Start to get martensite. You have MF. You don't have MF. Okay. So temperature at which transformation finish is called martensite finish or MF. So you have a starting temperature and low temperature. So what you can see, this black line is that as you increase the percentage of carbon, the temperature drop a little bit. Huh? So if you have more carbon, means it's a bit harder for the martensite to form, or it will slow down the time to form martensite. Okay. Okay. In the industry, the martensite, after they cool down, after they squeeze, then they will reheat at a temperature below the transformation temperature, 727. So in the industry, after they squinch, they will go through one more process. They will reheat it just below the eutectoid temperature. Okay, this one you read lah. This one you read. It's just again, it tell you what happened if you increase the carbon percentage, what happened to the crystal structures. Okay. So it will show you how BCC is gamma, right? So BCC, how it changes the BCT. So in a BCC, FCC, gamma is FCC. So previous in chapter 1 or 2, you already given the crystal structure A and then the radius of this one. So there is a gap, maximum gap you have is 0.01 something nanometer. BCC in alpha is 0.072 is here. Right? Or even here, this place here. So carbon is 0.54. It's very hard to go inside this one. So rapid cooling, rapid cooling, you shrink down, then you reduce the spacing. So this is the hardness versus carbon. Try to observe the relationship between hardness and percentage of carbon. So you have if you have more carbon, the hardness increases. If you increase your carbon, hardness will, on the graph here, you'll see the line go up. The line go up. Means if you increase more carbon, hardness will increase. And you need to be careful if you work in the material. You add carbon. Carbon is a brittle structure. Means you give your ductility and toughness will decrease. Carbon is something that brittle is like a concrete. It's good for compression, but not good for tensile. You want to pull it, it's very, very easy. If you have more carbon. But you want to compress it, then it's have more strength in compression. So this is a chart. If you have different type of alloy here, this one is plain carbon steel. So you go and buy some raw material. You make sure you check. Make sure you check. My first job, I work as a project engineer. So I deal with quotation. I deal with prototyping for precision metal stamping, for hard disk, for car seat, and all this. So just pay attention to the technical drawing that you receive and the material that you need to use. When you deal with customers that deal with precision, just pay attention to the material that is specified in the technical drawing. Sometimes they will assume you do not read the type of material. Get trapped for the costing. Because you sign the contract already, you must deliver. If you cannot deliver, you have to pay the fine. You break the contract already. Okay. So just pay attention to the material. If you cannot do it, just advise to your boss, say we can do, but we need to increase the quotation price or your cost. You just need to highlight this one. Then you let the boss decide whether you want to do or not. Okay. Okay, so the rest is quite straight direct, right? Okay, this is a simplified diagram. So austenite is gamma, right? Gamma. So gamma, you get these three types of metals. You have pearlite, you have proldetectoid, you have bainite, you have martensite. So you gamma, you rapid cooling, you get martensite. Then you reheat it, you become tempered martensite. It's still a martensite, but the industry give it one more name called tempered. Okay, then you have a American system, AISE. There's a 4-digit that I show you on the graph there, right? So what I mean by all the digit? So there are 4 code. First 2 digit, they are the steel type, and last 2 digit, they are percentage of carbon times 100. So for example, if 1010, 10 is a plain carbon steel, then with 10% or 0.1% of carbon. Okay, so 5120, 51 is a chromium steel. 20 here is 0.2% of carbon. Right. So here is just a roughly introduction. If you go to industry, there's a table for you to refer. Then there's another system. First one is American system. Second one is a British system. British system, they will give you one alphabet between the number. So for example, you get 070M20. So 070 is a carbon or carbon steel. M is a mechanical property specification. 20 carbon steel of 42%. So when you read code, make sure you deal with the correct code. Each country have their own code. Okay. And there's another one is called UNS, Unified Numbering System. So for example, you will see UNS something, UNS A696061. So for example, aluminium 6061, American system. And then if your customers use UNS, there's an equivalent meaning. So 601, if you use UNS, you use UNS A96061. And there's a code for each type of steel that you have. Okay, we have a short break here. We later will continue standard steel. So. Can you guys continue? We have 10 more slides. Okay, now we continue lah. 10 more slides. Okay, the next one, standard steels, that we are commonly used to prevent what? Normally, what case you use standard steels? Rusting, corrosion. Okay. So what is the so different between what the additional material that you add in, then it becomes stainless steels? Is this person or this element here, chromium? If you add chromium, you are making stainless steels. Right? From the normal carbon steel, you add chromium, you become stainless steels. Right? So yeah. So the rest you read lah. Important is once there's a chromium, you are entering into stainless steels dimension. You have a stainless steels 4 types: ferritic, martensite, austenitic, partition, hardening. So this one, it depends on the phase diagram also. Okay, so the first one, ferritic is alpha. So if you have alpha, you have more ferritic BCC, then you are creating a ferritic stainless steels. Means on the phase diagram, you play with the percentage of chromium, and then you observe the change of alpha or gamma to alpha, and then you get the things. So chromium crystal structure is BCC. So again, how you do previously, we have mentioned one rules. If you want to mix 2 elements together, one of the rules is that it must have the same crystal structure, so that it's more easily to park inside the space there. So in this case, we use chromium park into BCC crystal structure. All right, so this is the schematic diagram. So you have ion, you have chromium, you have carbon. If you take out chromium, it becomes carbon steel. You put in chromium, it becomes standard steels. Yeah. You take out the gold color or the chocolate color here, you take out, it become plain color, become plain carbon steel. You put in chromium, becomes standard steels. Okay. This is a phase diagram. It's quite direct. Again, it might be a bit special shape, but still you focus on liquid, you focus on alpha, Fe3CO, and there's one more, sigma here. Sigma is another type of solid that you get. Okay. Yeah. So again, there's a table. If you do with this kind of material, you have the composition, the material strength, and so on. For mechanical engineer, we are more focusing on the material strength or material properties, right? And so on. There's a long list of that. So there's a certain chromium, and let's see, I need to highlight here. Phase diagram here, bottom here is chromium, not carbon anymore. Don't refer to the correct diagram. So don't always assume you'll get carbon for your x-axis. Read carefully. Although this one sound C like a C, big C there, it's a C and a small R there, chromium. Okay. And if you see carbon here, normally it won't go past 6.67%. If you see a C here, normally maximum value 6.67%. Okay. So the rest you read just for info, right? So there's a certain temperature, then you get something. So the rest you read, right? So again, stainless steel is what you mentioned just now. Stainless steel, you have authentic stainless steels and so on. So they are good in corrosion resistant. Corrosion resistant. You have a few type, right? Just now, authentic, ferritic, metensite. So authentic, they are good in corrosion compared to the other two brother because of carbide, right? So carbide there. Okay. So with this, we conclude chapter 9. Okay, we have a 10 minutes breaks. We continue after 10 minutes.